In this lesson, we're going to be looking at Objective 1.5, Atomic Structure and Electron Configuration. So the learning objective states to represent the electron configuration of an element or ion of an element using the Aufbau principle. There's actually going to be a lot of different principles and rules we're going to talk about today, so it isn't just limited to this one principle. So let's first talk about Coulomb's law. Coulomb's law, I just want to say its equation is on your equation sheet. So Coulomb's law is used to calculate the force between two charged particles. For this unit 1, we're going to specifically be talking about subatomic particles like protons, neutrons, electrons, specifically protons and electrons because they're charged. Second unit, in unit 3, we're going to be talking about normal particles, as in if we had a cation and we had an anion from like an ionic compound, we can look at Coulomb's law to help us better understand that. So Coulomb's law is actually written as force and showing that there's this equal relationship, Q1, Q2 over R squared. F stands for force. This Q1 and Q2 represents charge, and then R squared is going to represent radius, but in the sense of atoms and subatomic particles, we're talking about distance. So one thing that Coulomb's law also helps us understand is that when we talk about things being attracted, we're talking about electrons and protons. When we're talking about things repelling, we're talking about an electron with an electron or a proton with a proton. All right. Think about a magnet when we talk about Coulomb's law. So I want to talk about a few things with regards to the force. Okay. As the distance between the charges increase. Okay, so here, if we increase the value of R squared, what does that do for force? So because this variable is on the denominator and we're looking at its relationship with force, this is actually an inverse relationship. Increasing this will cause a decrease of the force. So here, decrease. So here, as the distance between the charges are going to increase, the force of attraction will decrease. Then, when we're looking at as the number of protons increase with a constant distance, so here, if we increase this variable, how does it affect this variable over here? Here, this is a direct relationship. So if we increase the protons, so increase the charge, we will increase the force of attraction. So force of attraction increases. One thing I like to think of it to memorize that one is if I'm increasing the charge, the number of protons, I like to think of it as I'm getting a bigger magnet. Larger magnets are going to have larger forces of attraction. So when it comes to Coulomb's law, knowing that the force and distance have an inverse proportional relationship. While force and charge, so Q1, Q2 charge, have a direct relationship. Directly proportional relationship. I want to make sure they both said the same proportional word. All right. Now, you'll never need to calculate this, like I said, but you will need to reference it, especially when we get to the conceptual side of this in Objective 1.7. All right. Our next topic to talk about is effective nuclear charge. So effective nuclear charge is denoted with Z subscript EF. We call it ZEF. I don't know who came up with the Z, but the EFF is talking about the effective part. When you think of the word nuclear, nuclear is referencing the nucleus. So nuclear charge is talking about the influence of the nucleus on the electrons. Specifically, these electrons, you'll mostly look at it as the valence electrons, but you can look at it as a whole in general. So going off that first bullet point, remember that electrons are repelling one another, especially when we're talking about on the atomic scale. So with this screening and shielding, right now I have the picture off to the right, I'm just going to do a quick Bohr diagram of lithium, because that diagram is talking about lithium. These two electrons right here are considered my core electrons, while this one right here is considered my valence electrons. Remember, valence electrons are the electrons found in the outer ring, while the ones, again, in this case, we only have one energy level for core electrons, but we could have more depending on how many energy levels we have. So those two core electrons are actually going to be shielding your valence electron from feeling the full pull of the nucleus. It's almost like, hey, we're closer, we're first in line, okay? So if you ever wanted to find nuclear charge, you could actually calculate it. And so if you wanted to calculate the nuclear charge, you take the total number of electrons that your element has minus the number of core electrons. So based off this lithium example, here I would do Zeph as I see a total of 3 circles, 3 minus, and I see 2 electrons as core. So the Zeph charge for this is +1. Now, we'll talk more about nuclear charge, but the higher the Zeph, the larger the force of attraction. An attraction coming from the nucleus to your valence electron. So the higher that Zeph, there we go, the higher the Zeph, the higher the force of attraction that your nucleus has on its electrons. Okay. In atoms and ions, the electrons can be thought of being in something called shells. To us, we can just say energy levels. And subshells are going to be just sub-levels, as described by the electron configuration. So inner electrons, like I had mentioned earlier, will be our core electrons, while our outer will be our valence electrons. So going back to energy levels, remember I said these are called shells. These are going to be rows on periodic table. So if you grabbed your periodic table right now, which I kind of have one right here, every single row indicates what energy level that is going across. So here we would have up to 7 energy levels that an element atom could have, okay? Our sublevels, our subshells, are going to reference, oh, I have periods over there. Here they're going to reference blocks on the periodic table, and we have them labeled as S, P, D, and F. So if I scroll back down to this section right here is called our S block, all right? I'm not going to get into too much details about talking on a quantum scale and level. Our S subshell actually has the shape of a sphere on a 3D plane. Now, again, sorry, you can't see that. Here, I'm trying to draw on a 2D plane, trying to draw a 3D structure, so don't worry so much. But S, sometimes people memorize it by the word sphere. Next is going to be the P sub-level or subshell. Here, the P is going to be right here in the green shade. Here, the P sub-level actually looks like this. And again, I'm trying to draw on a 3D scale. It looks something like this. Then we have the D, and then we also have the F. And I'm not going to draw what those would look like on a quantum scale, but it would be kind of something similar to P, but there would be more of them. I do want to note that the S, like I said, people memorize it as the sphere, and P as the peanut, because those kind of look like peanuts. All right, going back up, the last thing I want to put is orbitals. So orbitals are specific areas of probability for an electron location. One thing you do need to know is one orbital can hold 2 electrons total. Also, just kind of to help you based off terminology, another thing that the AP test likes for you to say for energy levels is the principal quantum energy level. Once you get off to college, they'll denote this by the letter N. So like N equals 1 means that that's the first energy level. N equals 3 would be the third energy level. So go into the sublevels. So the S sublevel, that sphere, only has 1 orbital. So therefore it could only hold 2 electrons, knowing this part right here. The P sublevel has 3 orbitals and can hold 6 electrons. Here, if you saw this picture I drew over here, the reason that it's 3 orbitals is because that is 1, this is 2, and this is 3. And you can see there are technically 6 spots that those electrons can be. And lastly, so then we have the D sublevel. There is 5 total orbitals. 5 times 2 would be 10 electrons total. And lastly, the F sublevel has 7 orbitals, can hold 14 electrons. Going down here, even if you forget how many that sublevel can hold, just count however many elements are in that block on the periodic table. So the S block, if I put a line all the way down, there are only 2 electrons in each of the energy levels for the S. For the D, if you counted all the way across, there would be 10. P would have 6, F would be 14. All right, there's a few principles and rules that I want to talk about before we start some problems. The first one being the off-bow principle states lower energy levels are filled before higher energy levels. So here, how I would like for you to think about filling out an electron configuration, read the periodic table like a book. So what that means is we're going to start in the top left-hand corner and we're going to read left to right, and we're going to go down, down and through all of the rows till we get to the element that we're trying to make an electron configuration for. And just to kind of help you put things together, what is an electron configuration? It's basically a code to tell us how where electrons are for that atom, okay? And it's basically, again, it's a specific code, and it can correlate to a neutral atom. The Pauli exclusion principle states that, trying to zoom in, no 2 electrons can occupy the same space in an orbital. So electrons are assigned different spins. And we'll talk more about this, but basically it just means they have to be going in different locations. So if you're talking about the sphere and you have 2 electrons, you need to have one going one way while the other one is going the opposite way. All right. And we denote that with arrows. We show one going up and one going down. We will talk about this in a couple of sections of these notes. Lastly, Hund's rule, atoms are lower in energy if electrons having the same spin are maximized. So what that means is fill one orbital first before doubling up. So what that means is if we are focusing on the 2p, and again, I'll get more into details about this. Instead of, remember the p sub shell sublevel is going to have 3 orbitals total. So if this was 1 orbital, 2 orbital, 3 orbital, add 1 into each one to help maximize energy before you start doubling up. This is good. We don't want this to happen. Actually, let me remove this one for purposes. Here, you don't want to do this. Oh, sorry, you can't see. Here, it's better to put 1 in each of the orbitals rather than trying to double that up, okay? All right, so let's try to write an electron configuration for each of the elements, okay? So first, let's start with manganese. So I want you to find manganese on the periodic table, okay? And I want you to circle it on your periodic table, manganese. You'll find it in group 7, and it should be in the 4th row. So how we start this is, again, we're going to start with hydrogen in the top left, and we're going to move across and go down all the way to manganese. So following this up here, again, this is a stretch, but manganese is kind of somewhere around here, okay? So we're going to first start this way, and I would say that the first row is complete as 1s2. I do want to note, I realize I should probably show this. The number that is in front of the letter indicates the energy level, so what row it's in. This letter represents the sublevel or the subshell, and this is the number of electrons. So remember, our S can hold up to 2, our P can hold up to 6, the D can hold up to 10, and the F is 14. All right, so next, I would say the 2s2 is completely filled. 2s2. Continuing across, I would go all the way across the 2p. Remember, the 2p can hold up to 6. Next, I come down. The 3s is completely filled. Going across to the 3p. 3p6 is filled. I then come back up. Then I go down to the 4s. The 4s2 is completely filled. And then lastly, you will note that the D block actually drops down in energy level. So just because now we are entering the 4th energy level, and that's where the D first shows up, the D block actually brings its electrons down 1 energy level. So even though that's the 4th row, the D subshell will be found in 1 less. So here, this is the 3D, and then count however far manganese is, which it should be 5. It should be the 5th element in the D block. Just to kind of give you some fun fact and information on why our transition metals do this, because the transition metals are in the D block. Transition metals, from your basic chemistry class, you should have learned that they have multiple charges. Okay, for example, copper can be copper 1, copper 2. Iron can be iron 2, iron 3. The reason they're able to do this is they end up shoving their electrons down in energy level to make room to have multiple charges. Okay, it is a crazy property that these metals can do. It is what it is, okay? Just try to remember that that D block, even though it was the 4th row, 4 minus 1 is 3. And even if we were in the 5th row, that would be the 4D, okay? All right, I'm going to try number 3 with you, and then I'm going to have you try number 2 and 4, okay? So let's look at Al3 positive, okay? Starting now, I am not going to be referencing coming up here. So make sure you have your periodic table following along, okay? So Al3 positive means that this is a cation and it lost 3 electrons. So I'm first going to do the electron configuration for aluminum just because we are learning right now. Obviously, once we learn how to do this, we don't have to do this step every time. So first things first, let's get aluminum's neutral electron configuration. So here, the 1s2 is complete. Then the 2s2, 2p6 is complete. And then I have 3s2 and 3p1 because aluminum's the first one in the 3p. Now I need to remove 3 electrons because of that positive 3 charge. So here we always remove electrons from the furthest energy level, okay? And so here I'm going to remove this one and I'm going to remove this one, okay? So here this actually ends up making aluminum 3 positive, 1s2, 2s2, 2p6, because we removed those 3 electrons, okay? All right, why don't you pause the video and try the other 2 out yourself? All right, so let's look at the answers. So phosphorus was found in the 3rd row, which is in the 3p, so that should have been your last part of the electron configuration. And so here we got to the 3p3. Number 3, bromine. Oh, sorry. Yeah, bromine. Oh, I realized I should have done number. It doesn't matter. Number 3 with the bromine. Here I got the full neutral bromine electron configuration. Since it's Br -1, that means we gain 1 electron. So here, instead of removing from that 5, we'll actually add 1 and make that 6, 4p6. All right, moving on. One thing that I want to do based off terminology is tell you the difference between excited state and ground state. So an excited state is talking about ions, so charged atoms. So just like question 3 and 4, the Br -1 and aluminum 3 positive. This is technically the excited state for those atoms, okay? Next, the ground state is going to be the neutral atom element. So like the first 2 examples, I think we had manganese and phosphorus from the ones above. Those are just in their ground state, okay? Next, isoelectronic. This is species with the same electron configuration. So I want you to realize when we have ions, they are trying to become like a noble gas, okay? And so now granted, the transition metals might look a little funky. So in this example underneath, neon is going to be our noble gas, and it has a electron configuration of this, which means the following ions are all going to have 1s2, 2s2, 2p6, okay? All right, why don't you pause the video and try this one out yourself? All right, so in this example, we have Cl-1. So we're trying to see from that list which one would have electron configuration similar to our chloride ion. So first things first, I took the Cl-1 and got its electron configuration. And so then, looking through all of this, the one that actually matches up will be the answer choice C, K positive. And actually what's funny is A, B, and D actually all have the same electron configuration, but it doesn't match up with our chloride. I guess you could have also looked that my example choices for A, B, and D are also up here as well. That was an oversight. All right, moving on. Now we're moving on to noble gas configurations. So noble gas configurations, think of it as a shorthand. I don't know if you've noticed already, but it can be a little tedious writing out full electron configurations. Now, if a test question asks to write out a full electron configuration, you need to write all of it. If it just asks for an electron configuration for something, you are more than welcome to do a noble gas configuration. One thing I want to just put to note about how to do this, remember a noble gas means that it has a complete energy level. So that entire row is complete. So you can denote a complete energy level by using brackets and putting noble gas chemical formula inside. And so here, if you look at this example that I have, carbon, before carbon, I believe it looks like this. I'll just write it right here. 1s2, 2s2, 2p2. So looking at our noble gases, helium, neon, argon, continuing, here the 1s2 is referencing helium. So me putting brackets helium omits the 1s2, which then to fill out the full noble gas configuration, you write whatever remains. So here you can see I have helium and I wrote the rest, 2s2, 2p2. In this sense, it's a little bit easier to read, and then you just have to tell yourself, oh, I just have to look at the second row to find what this noble gas configuration, what element it relates to. So let's look at this right here. I have calcium, titanium, and chromium, okay? So let's quickly fill out the electron configurations for this, okay? So why don't you pause the video and write the complete full electron configuration. So just pause the video and then press play and I'll have it completed. All right, so looking at this, I have the complete electron configuration for all three. You will notice they are all in the same energy level. And here, I can tell this part right here is where we have a full, complete energy level. So I'm going to write underneath complete energy level, which, by the way, find out which element, which noble gas this corresponds to. This corresponds to argon's electron configuration. So to put the shorthand, all we would have to do is put AR, which AR is referencing what I have highlighted, and then whatever remains that was not highlighted, so 4s2. And if I do that for the next one, I have argon in brackets, 4s2, 3d2. And then lastly, brackets of my noble gas, and then whatever remains to indicate what element I was working on. Here again, this is a shorthand. You're more than welcome to use it if you are able to based off wording on the test, okay? All right, now let's finally talk about orbital diagrams. So here we can represent the electron configuration in a slightly different way with an orbital diagram. And so it gives the same information that an electron configuration does, but it actually will symbolize electrons as arrows and the orbitals as lines or sometimes boxes. I tend to lean towards the lines option just because I have more time to do stuff. So unlike an electron configuration, yeah, you know what sublevel it is and how many electrons are in it, but you never actually look at the orbitals, okay? So one thing to note, the direction of the arrow pointing up or down represents the orientation of the electron spin, which we actually talked previously when it comes to the Pauli exclusion principle. Then you must start with an up arrow first in all of the orbital boxes, then you can use a down arrow. So stay consistent. We don't want two up arrows. We don't want two down arrows, okay? So just kind of bringing back this little piece of information. Remember, one orbital can hold 2 electrons. So let's say I want to do an orbital diagram for oxygen. So looking at oxygen on the periodic table, I know that it has this electron configuration, okay? So if I wanted to draw an orbital diagram to talk about oxygen's electrons and orbitals here, for every orbital, you will draw a line because that's what is stated, oops, sorry. And an orbital is designated by a line or a box. So since the S can only have one orbital, I drew one line. Then I have the 2s. So here I have one line. But then I get to the 2p. I know the 2p can hold, sorry, it can have 3 orbitals. Okay, right. So now you fill in and making sure that we also follow not just the Pauli exclusion principle, but also Hund's rule. Okay, so here I'm going to put one up arrow, one down arrow. Filled, moving on. 2s, one up arrow, one down arrow, done. Now when it comes to the next part, remember we need to put, this goes with Hund's rule, we need to put one in each separate orbital before we can start doubling up. So here I'm going to put up, up, up. That's only 3. I need to add 4. So I will do 1 down. Okay. You might see on your homework that I denote that these orbitals are different by putting px, py, pz, just indicating that these are 3 different orbitals, x, y, and z, in the 2p sublevel. Okay. And yeah, this is how you would do an orbital diagram. Just the last few minute things that just to summarize everything that was important. Always do lower energy levels first before higher energy levels. So just making sure that you read left to right like a book when you look at the periodic table. Orbitals will fill in this order. Totally fine to reference that as well. Also knowing that orbitals can hold no more than 2 electrons. This is so important. And knowing that their spins are going to be in opposite directions inside that orbital. Last thing before I end this video, let's talk about exceptions, okay? So remember, we always remove electrons from the farthest energy level because you can't just reach inside an atom and pull out core electrons. So I want to focus on nickel first, okay? So let's do the electron configuration for nickel. 1s2, row is good. 2s2, 2p6, second row is good. 3s2, 3p6, third energy level is good. And then we have 4s2, 3d8, okay? So looking at this on a Bohr model representation, and again, don't worry too much about Bohr models, but I will use it as a reference here. So the first energy level, remember, that's where the 1s would be found. In the second, the 2s and 2p. In the third, the 3s, the 3p, and the 3d. And lastly, the 4s. Again, how I knew where to put this is I looked at the first number listed, okay? Just to kind of reiterate again, Niels Bohr had the right idea about the Bohr model to help us understand this quantum mechanics of chemistry on a more easier conceptual way. This is not how the atom would look like because we saw that based off the shapes of the S, P, D, and F, but it isn't a bad idea to reference if we're trying to understand things. So moving on, let's say that we have Ni2 positive. Where do we remove electrons? So here your first instinct is to look at the last thing written in the electron configuration. Well, after drawing this Bohr model, you see that the 3D, remembering it's in the third energy level, you need to remove from the farthest energy level possible. Here, that would be, sorry, that's lagging. It has to be the 4s, okay? So we will actually be removing these 2 electrons right here. So to write the new electron configuration for this nickel 2 positive, it will be everything but the 4s, okay? And just to make note, always remove electrons from outer energy levels and work your way in. Okay? All right, I have this example with silver. I will tell you silver is actually a fixed charge. we'll be working with silver +1. So why don't you write the neutral silver electron configuration and then do what silver +1 would look like. All right, so let's go over this. So here you actually only need to remove just one electron. We don't have to remove both of those electrons in the 5s. So here it actually just goes from 2 to 1. So here, again, just remembering that the 5th energy level would be the furthest one out. The 4D would be in a closer energy level. Okay, now just to kind of like think about this, let's just say, which it wouldn't, let's say silver had a +3 charge. After we would remove these right here, we can start removing from the 4D in that case. But silver doesn't have a +3. We could use this for an example like iron 3. Okay,